Ranjani, BMS Production Unit in Bangalore. My guides are Mr. Sudhir from WorldServe Education and Ms. Ranjani. The topic of the paper is optimized negative blob recognition for imaging-based touchscreens. And I'll be starting off with an image of what we see in every day, what we do every day. And I think that is going to go on in the future as well. Our world moves in micro and nanoseconds, and we just don't get time to complete our work, and therefore we try to get as much work done as possible during food. This is something common, I feel, but I know it's not always beneficial, and I'm sure that all of us would like less omelets on our laptops. But what is the solution for this? One solution can be written on the table. That is an intelligent table that on which we can work on, and we can also eat on, and it's intelligent. That is, it can detect your touch and it can differentiate it from the touch of inanimate objects. So a tabletop computer, if you're going to go for the capacitance or resistance based tabletop computers, what is the problem is the size. Capacitance touchscreen of that size will be very, very huge. So an image processing touchscreen is a better option. And this is the setup we use. While going towards this tabletop computer, the first thing we have to do is find the point of contact of the finger. And so this is the setup we use. A normal thermocol box is being used. We use a glass pane for the touch surface, and a tracing paper is used, which will obscure the background and help us in fingertip detection. And the camera is placed inside the box. The camera is normal web camera, and it has 4 LEDs. 4 LEDs which will help us whenever there is dim lighting conditions. And one thing is, we're not using frustrated total internal reflection here, which is used in most of the cases. And certain sample pictures are shown here. One thing that is to be noticed is that there is a sharp difference in intensity around the edges of the finger, which is not there near the shadows. That is, there is a gradual change around the shadow, but there is a large change near the edges of the finger. And the last one is when the LEDs are switched on. As you can see, the finger appears white. That is, the background is dark and the finger appears white. So we can apply this, we can use this in our algorithm, which is what we have done. This is a portion of the edge of the finger that is zoomed, and as you can see, there is a large difference, a large difference around the edges, which has been highlighted here. And but when the shadow is zoomed, as you can see, there is not much change. There's not much change. There is a gradual change in the pixel intensity. What we are doing is, basically, we take 2 pixels, one alpha, the current pixel, and one more pixel, beta, in the same column as alpha, but a certain number of pixels above the current pixel. And we use the image intensities of these pixels, the Y values basically. The subtraction of these will yield one value, another value, and this value, if it is greater than a certain threshold theta, we conclude that the current pixel alpha belongs to the foreground. That is, it falls under the area of the finger. If it is less than theta, then it belongs to the background. That is, it's either the tracing paper or a portion of the shadow. Now, the heart of the algorithm lies in this one subtraction. This subtraction is repeated for every pixel in the image, and therefore what we obtain is a binary image with 2 values. One for white, which says that it's the background or the tracing paper or shadow, and the other 0, black, which indicates that it's the portion of the finger. The flowchart of what we've done, So next step is deciding the theta and delta values. Now what we did is, first we arbitrarily fixed delta to be 5 and then varied theta. As you can see, the results are best for theta is equal to 10. And next, to decide delta, we fixed theta is equal to 10 and then we started varying delta. And again, what you see here is that the results are best obtained at delta is equal to 5. So now we have 2 proper values, that is delta, the difference in the number of pixels between alpha and beta, that is 5, and one more is theta, that is the threshold value for the image, that is 10. As you can see, it's working well for 3 results, and more experiments were conducted. It worked well for all of them. And so next factor in this is the performance. How well will this perform? I implemented this in Java on a Core Studio processor, and the results have been tabulated as follows in the table. One thing that is to be noted is that the time measured there, I've given the split up just for illustrations. Color conversion and segmentation removal is usually done in one step. So therefore the combined time is actually the largest time is the determinant. So therefore that can be done in, our algorithm will be done in 90 milliseconds, and any general algorithm. By general algorithm, I just took the example of Otto algorithm in this case, which is used for text detection widely. So that is performed in 125 milliseconds. So our algorithm is 15% better when used in Java. And we are currently performing research. We are extending this algorithm, and at WorldServe Education, actually two of them which are being performed are, one is multi-touch, which is again an extension of our algorithm, and another is pest detection in plants. That is a variation of our algorithm which is being performed. So concluding, we can say that this algorithm is accurate. It can be used in many places, and with the judge's permission, I'd like to show a 30-second video here. This is the setup which we use. The camera is placed inside the box, and the glass pane on which the calculator has been drawn. Actually, this is just for illustration purposes. The camera need not be drawn. The thing is that a projector can be placed next to the web camera, but that will be during the later stages. But right now, this is how it was done. As you can see, the buttons are being pressed, and corresponding properly it is being pressed. The calculator was developed in Java, and I think you can see that the correct answer is displayed on the screen for the operation. 8 plus 2 plus 8 plus 5 plus 2, that resulted in 15. So like in this way, there can be many applications that can be developed. One of them was calculator, as you just saw. One more can be the piano. There could be a gaming console developed, and the list can go on and on. And these are the references. Questions?